Okay, let me also present my screen. Does everybody have the slides for today? I love seeing these responses. You'd love to own a bakery. McKenna, I am with you on that. I love that. I love bakery. I used to be really into photography whenever I was like, had more time for it, and videography. So those are things that I would do. But whenever I think like, okay, what would I do as like with my life when I look back on it, like what would I want to look back on and say like, okay, I contributed, you know, I want to see like what y'all are thinking about that. I'll have to tell y'all mine at the end. I'll have to tell y'all my answer of what I would do and what I hopefully will do, because hopefully I can still do it. Travel to other countries. I love it. I love it. Hi, Roxy. Create opportunities for underprivileged kids in tough areas. I love that. That is so cool. This is a great, you know what? I like this question that I'm asking, because you guys are at an age right now where you can still ask this question and think, what would I do? What do I want to do? And you can change your mind and think about it and wrestle with it. But I think it's a good question to ask yourself, because you've got your whole life ahead of you. So you have the opportunity right now to do a lot of things with your life. Hey, Landon, what's your question?
Do you know how to make coffee? Because my mom says I had to make my own coffee.
Whoa, sorry. It's an Amber Alert. I do know how to make coffee. I love making coffee. I can send you a recipe.
Coffee.
Okay, let's talk afterward. I'll help you out if you tell me the details. Celine says, get a mansion, own 12 exotic animals, and get all the clothes me and fam whenever we want, whatever you want. I love that. That is so cool. I love all these responses. Get more dogs. That's so funny. Okay, I love this. Okay, does everybody have access to the slides, or do I need to send it one more time? Let's see here. We're gonna go ahead and get started because we got some stuff to learn today. Okay, get a mansion in South Korea. That's very specific, and I love that. That's very exciting. I would love to get a mansion in Japan. That would be not like a mansion, but like maybe more like of a traditional house there. I would love that. At least I'd love to travel to Japan. South Korea, though, that's really tempting as well. Okay, so let's go ahead and get started. I'm super excited y'all are here. I'm so glad. I love live class, so I hope that y'all enjoy it too. It's like I get nervous, but I like look forward to it so much every week to see all of you guys. I wanted to remind y'all that this is the school mission for iSchool, and it's my mission too, is to provide hope through educational options that promote a free society and cultivate moral and academic excellence. That's my mission, and that's the mission for the company I work for. And specifically with iSchool, is to provide hope through a virtual environment that's mastery-based, blended learning, a blended learning educational option that promotes free society. So we want y'all to know that's our goal, and if there's anything I can do to help you with that goal, I want to know about it. Okay, let's see. All right, now we're going to do some learning today. Are y'all ready for that? By the end of this lesson, you are going to be equipped to do these things, okay? You're going to know the base units for the metric system. You're going to hopefully know how to count significant figures and round with significant figures, and then how to use scientific notation. So these are the things that hopefully you will learn about by the end of this lesson, okay? You're totally fine, Emily. So first, we're going to talk about standards of measurement. So a physical standard is something that's used, it's a physical item that's a standard for measurement. These aren't very common anymore. For example, like when you think of the foot came about because people would literally use their feet as a measurement system, right? Another example is the cubit. The cubit is a length from a person's arm to their elbow. And so they would literally use their own arm to measure something and report it that way to get like a general estimate. There are some problems with that, right? If we're just using everyone's individual feet, we all have different sizes of feet, right? So the problem with a physical standard that's not like completely standardized is that it's different per person. And so if I say that something is 10 feet, it might be a lot smaller than somebody else, right? So this was a problem, but back in the old days, this is what they had and this is what they did. So that's why it was kind of problematic. Now, well, after that, it's not really now anymore. Standards were established like across, certain regions, and a physical item became the official foot. So they would have it like in a museum, and they'd be like, this is the foot, and it's 12 inches, right? And they would keep it that way. And this right here that you're seeing is the kilogram. Okay, so that is literally the standard for a kilogram, because that is the kilogram. And so everything else is based off of it, and it's like kept in this special place. And I think it's in a museum now because it's so valuable, because it's the kilogram. But this also became a problem. People would have to go to that location to compare their templates, right? And things can change based on heat. So like if you heat something up, it might get a little bit longer, right? And then it might get shorter again. So it's not really even then set in stone. So how can we have a standard? What can we do to make a standard set in stone against the test of time? So what we do now is, if you may already know this if you are interested in science, but all the physical standards for the metric system were replaced with calculated constants, like the speed of light. The speed of light is set as far as we know, and it doesn't change. And so there's no way that you can manipulate it. So basically they made all of the metric system standards now be set by something that is a constant that never changes. Yeah, I don't know whose foot it was based on either, Emily, because is 12 inches, is that like a standard foot? I don't know. Like, is that how long a normal foot is? I don't even really know. Okay, so a unit is a quantity with which other quantities of the same kind are measured. So what are some examples of units? Y'all throw out some units that you think of. Just any example of a unit. What do y'all think? Meters, yards, kilometers. I love all y'all's responses. There we go. A liter, hours. I love it. You'd said liter, and we're about to do that right now. Quarts, pounds, inches, pints. It could be anything. It could be people. That's a unit. Not very great of a unit, but cups, ounces, gallons, seconds. Exactly. Seconds is a unit. Pint. Anything like at the end of it's a descriptor that holds something to a standard, right? So looking at this picture, there's a lot of units for the same type of thing. This picture is all measuring volume, right? Look at this picture. Doesn't that look like it's all measuring volume? You can use quarts to measure volume, cups to measure volume, milliliters to measure volume, pints to measure volume, gallons. What else? I don't know. I think those are the main ones on there. So there are a lot of units for one type of thing, like volume, right? So there are a lot of different units. And since there are so many units, we have what we call base units. Yes, ma'am.
I just wanted to let you know that my brother Xavier Moore, he's in this class, and he's about to come on in a few minutes.
Gotcha. Thanks for letting me know. No problem at all. Thanks for letting me know. So basically we have base units now, which are like standards for like, okay, this is what we're going to use commonly. So like, rather than there being like 100 different ways to measure something, we're going to like have a normal, and these are our norms. So in the US, it's called the English system, and these are our norms right here. We measure distance with the foot, mass with the slug. Have you all ever heard of a slug? Because that's how we measure mass here. We don't really do it that much. Volume with the gallon, time with a second, and temperature with Fahrenheit. That's the English system, right? Okay. Everywhere else in the world, except like the US, and I think Mexico might also use the English system. I'm not sure. There's one other country that also uses the English system. Everything else really uses the SI system, which is based on metric. And so in science, we're also going to be using the metric. So you need to familiarize yourself with the blue one. The blue chart is what's really important here. And it's just a different set of units. Meters for distance, kilograms for mass. Something else to point out is that you can't measure distance with a kilogram, right? Like they don't transfer over. You can't measure time with a liter. So these units are like linear. They don't cross over. You can't convert between meters and grams, right? Because there is no like, it's not this, it's a completely different set of things, right? So just know you can't go from distance to mass unless you have like we'll talk a little bit more about density and things like that later in derived units. But I just wanted to note that. I'm going to go through some of these a little bit quicker. These are the different types of links here. We just talked about that. A derived unit is something that combines two of those things. So for example, area combines distance with distance. It does distance twice, length and width. So it's distance squared. So examples of that would be units of meters squared, centimeters squared, feet squared. Anything that's a length squared is going to be a unit of area, right? Another derived unit would be volume. Volume is length times width times height. So it's distance times distance times distance times distance. It's doing it 3 times, right? And so it's actually distance cubed. So examples of that would be centimeters cubed, meters cubed, inches cubed, liters. All of those things are cubed forms of distances. Density is mass divided by volume. So it's like kilograms divided by meters cubed. So you can look at the units to tell you what you're dealing with. The units will always tell the story of what is involved. If you see this unit like kilograms per meter cubed, you're dealing with something that is density because it's mass divided by volume. I wanted to include this slide because you have some questions on it in your lesson. This came from your lesson, so just know these are different forms of pressure, and you may want to refer to this slide later if you have a question about that. Just wanted to include that slide there. Pressure is force divided by area, and so these are the units here for it, though. These are the typical units for pressure. The next thing I want to talk about is accuracy versus precision, okay? So accuracy is how close a measurement is to the actual value, okay? So if you look at the first top left example right here, hitting the target is an example of accuracy. Accuracy is like comparing what you did to the true value of it, okay? The example on the right shows low accuracy, right? We are not hitting the target here on the right. Precision is not the same thing. Precision is how close your measurements are to one another. So this example on the right is actually very precise because I'm able to hit the same area, very close together. So even though it's not accurate, it's actually very precise. This is an example of accuracy, like it's kind of hitting the target, but they're all kind of in different places, so not very precise. This is an example of not being accurate and not being precise. So precision is how close measurements are to one another, and accuracy is how close you are to hitting the target. And those are things that people got confused on some questions on the difference between those two things. Okay, now we got to talk about the fun stuff. I've been excited about this. So y'all look at this ruler, look at this picture here, and tell me, if I asked you to report the measurement, what would you say? Let's pretend like it's in inches. So we're looking at inches here. Look at where that red line is. What would you report the measurement to be? Yes, ma'am, Aisha.
2.5 inches.
Okay, 2.5 inches. Okay, so y'all think 2.5, 2 1/4, so 2.25. Adam says 2.3. Catherine says 2.2. Okay, so let me see what my next slide is. Hold on. So let's do ruler 1. So let's look at this here real quick. So look, this has 10 tick marks between the 2 and the 3, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got 10 tick marks. So 2.5 would be right here where my mouse is. 2.5 would be right here at the 5th mark, right? So let's count. It's past 2.1. It's past 2.2, but it is not yet at 2.3, right? So maybe it's like 2.21, right? Maybe it's something like 2.21 because it's past the 0.2, but not yet at the 0.3, right? What if we only had ruler number 2? What if we had less tick marks? How could we report that one? Well, if I'm reporting this one, I don't really know exactly where it is. I would say maybe like 2.2 or something like that, like something close. It's definitely not at 2.5. It's definitely not at the halfway mark. So I might guess, okay, maybe 2.2. I can see that it's not at the halfway mark in my mind, right? So you can see that the more tick marks you have, the more precise you can be. You can have more digits, right? So this is an estimate. The last number is going to be an estimate. We all should eventually see that this should be 2.2, but that 4 is kind of being estimated, right? That we don't know if it's 2.24 or 2.21. It's an estimate, right? And the same with this one. We don't know exactly where it is. So this is actually an estimate right here. So you can see that the top ruler is more precise than the bottom ruler, right? And I want you to see that in every measurement that you take, one of the digits, the last digit, is going to be estimated. We're not really sure what it is. So if I were to measure the length of my coffee cup here, I might say that this is like 6 inches, right? But it really could be like 5.99999987654 inches, right? In reality, in real life, measurements are not perfect. And things are typically not exactly 6 inches. The ability for this to be 6 inches to be 6.0 to infinity is like impossible, right? There's no way that this is 6.00000 inches. There's probably a little bit of a difference there, right? So in science, numbers are estimated because there's no way that we can report all of them. Whenever you're measuring something, you can't report all of the infinite zeros at the end of it. We're going to estimate to some extent and try to get a rough estimate. So let's look at this one. Where do you think the water goes here? So let's count from the 5th. 5, 6, 7, 8. So it's between 8 and 9, right? Y'all see how this water is between 8 and 9? So Natalie's thinking 8.5. I might agree. I might say 8.5, right? But I would never say that that's 8.567 because there's no way for me to know that. I already am guessing on the 5. I'm kind of guessing on that. It could be 8.4. It could be 8.6, right? So the last digit is kind of estimated. So Natalie might say 8.5. Emily might say, I think it's 8.3. And Celine might say, I think it's 8.6. The last digit is going to be estimated. So that's why we have significant digits. I want y'all to know that because some of y'all are like, why do we have to learn this? Do y'all like my drawing of these engineers? I drew this for y'all, so I hope you appreciate it. Okay, perfect. So I'm going to give y'all a scenario here of these 2 engineers, okay? 2 engineers. I'm going to read y'all a story time. So y'all just sit back and listen. 2 engineers work for a construction company, and they need to order bricks for a project. One puts in an order for bricks that are 0.55 feet in length. So he orders bricks and he writes the order and he says, I need bricks that are all 0.55 feet. And the other puts in an order for bricks that are 0.550 feet in length. Which order do you think is going to be more complicated to make? What do y'all think? The 0.55 or the 0.550, or should they both be the same? If 2 engineers are making an order, Adam says that 0.550 is going to be more complicated. I'm seeing some saying they're the same. Landon saying 0.55. Courtney saying 0.550. I'm seeing a few 0.550s. Why do y'all think that? Why are some people saying that? Let me tell y'all, you might think 0.55 and 0.550 are the same. The 0 does not make a difference. Like, it is the same number, right? The numbers seem the same, but a 0.55 foot brick is estimating to the hundredths place, right? He's estimating that last digit. And the 0.550 foot brick is estimating to the thousandths place, right? So the second order will require a machine that goes out to that place, right? It's going to be more expensive. He's going to probably pay like 5 times the price because they have to have a more expensive machine. So this is why numbers matter in real life for engineering, right? Or for science or for making orders. Like if you need a tolerance level that's more precise, then you're going to have to pay more for it. So the digits you put matter. 0.55 is the same as 0.550, except that 0.550 is a little more precise. It's going out to one more digit, right? So does that kind of make sense to y'all, or are you like, that's super confusing, I have no idea what's going on here? Making some sense? Okay, awesome, awesome. All right, let's see here. What do I have next? I'm so glad that makes sense to y'all. All measurements have uncertainty. I'm just kind of repeating that information. So that's why we have to have rules. Some of y'all are like, why do we have all these silly rules for rounding? It's because digits actually do matter in real life. Okay, so here are the rules for counting. If you did the lesson and you were overwhelmed, I simplified those rules to right here. Okay, these are the rules for counting significant digits. So if the number is not a 0, then all of the digits count, right? Every single one of these digits would count. If the number is a 0, but it's being sandwiched in between two non-zeros, it's also going to count. So how many digits do y'all think are in the number 104 right here? How many digits are significant here? All 3, exactly, great job, 3, all of them count. Because the 0 is going to count whenever it is being sandwiched. The next rule is that if the 0 is at the end, it will count if a decimal is present. Okay, so the decimal has to be there for the trailing 0 to count. No problem, Elijah. So how many digits do y'all think are significant right here? If you count these. What do y'all think? Y'all are busy counting? 5, right? 1, 2, 3, 4, 5. All 5 of these digits count, right? I don't know if y'all can see my mouse or not. Unfortunately, you can't. But the 81.200, 81200, all 5 of those count, right? The next example, oh, I kind of accidentally flipped these. So we're going to flip the examples. But if the trailing 0 has no decimal, like in the number 100 with a comma at the end, that's a comma. In the number 100, there's no decimal place. And so only the 1 counts. And so there's only 1 significant digit in the number 100. So if the 0 is at the end, but there's no decimal, it doesn't count at all. And then the last example is a leading 0. Leading zeros never count. So in the example 0.0051, only the 5 and the 1 count. Okay. So if you have any questions about those, stick around after and I'll go through them a little bit more with you. But I wanted to kind of just review those rules with y'all. Let's practice a couple real quick. So how many significant digits are in the number 12? What do y'all think? 2, right? They're all non-zeros. They both are significant. How many are in the number 700,000? Okay, so trailing zeros do not count unless there's a decimal present. So those trailing zeros only count with a decimal, and there is no decimal here. And so only the 7 counts. All of those zeros don't count toward being significant. They're kind of being estimated. It could be like, it's like 700,000 about, right? All of those zeros are kind of being estimated. So only 1. Oops, I gave you all the answer. What about this one? 0.00620. 3, the leading zeros don't count. The 0.00 does not count, but the 6, the 2, and the 0 count afterward because trailing zeros count when a decimal is present. Let's do one more example. 10,006. What do y'all think? So those are all sandwiched zeros, right? They're all sandwiched. And so all of them count. 1, 2, 3, 4, 5. 10,006, right? All of them count. So that's how you count. Here are some more examples. When there is a line above the 0, it validates all of them. It makes them all count. So if you see a line, it means that all of the zeros up to that point do count. So that's the difference between these two numbers here, just so y'all know. So you can look at those examples if you want. When you're rounding, the way that it works, if you look at my example here, when you're multiplying two numbers, you count the digits. So y'all see how this one has 2 digits and this one has 3? Y'all see that? Right? So when we multiply, we might get this number right here, 16.815. But I have to round to whichever number is the lowest. 5.7 only has 2 significant digits. So I have to also round to 2. So as our last thing here, well, we'll see what we can get through in the next couple minutes, but I have a little bit more slides here than needed so that some of y'all who are ahead can keep looking through the slides. So please look at these slides for reference for learning material for you, but know that we won't get through all of them today, and that's totally okay. I think I did this a little bit off. What if we needed to round this number to only have 2 digits, what could we round 12.6 to? Would that round down to 12 or would that round up to 13? Exactly, it would round up to 13 because this number is a 6, right? Anytime it's 5 or higher, it'll go up. What about the number 98.45? What will that round to if we only can keep 2 digits? 98, great job, Autumn, because you look at the 4. The 4 is not 5 or higher, so it's gonna just stay at 98, right? And then I have 8.0891. What would that round to if we can only keep 2 digits? 8.1, right? Because this 8 right here is higher than 5. And so it's going to bump up that 0 to a 1. It's going to become 8.1, right? You can look at these other examples here. Actually, I need to fix this one. I'll fix it after class. This answer should, oh no, that answer is also correct. So look at these examples if y'all need help with this for like how you round. That's easy for some people, and actually it is kind of confusing for others, and that totally makes sense if it's confusing for you. So just know I'll practice with you if you want. And this is just more practice with rounding, like how do you round with significant digits? There are different rules for adding and subtracting. Do y'all remember like place values? You can look at this slide to look at place values if you want. And it reminds you how those work. And then you can see how you round with this as well. But I'm gonna give y'all just one before y'all leave today. If you wanna stick around and ask more questions, you can. I have this information here for y'all to learn, but I want y'all to know I have some tutorial videos here at the end and some significant, some handouts here at the end too. So that y'all can look at this information yourself and learn from it. And if not, you can always come to my classroom for help, and I will help you with it one-on-one. These are the times that I'm in my classroom to help you guys. So with that being said, I'm gonna stop here for today. I'm gonna stop recording. But if any of y'all have any questions, you can stick around. Bye, have a great day, Megan. Bye.